All right, so today we're going to look at probably my favorite topic within the realm of probability, expected value. Okay, so what expected value is it's the idea of when you play a game that has some sort of like a chance aspect to it where you win or lose money. Okay, your expected value is how much you expect to either win or lose if you play the game many, many times and you don't change anything. So you always make the same bet. Okay. So it's sort of like saying, okay, like if you go to a roulette wheel, right, and you keep betting on the same square every single time, right? How much do you expect to win on average per game? Like you might in any one particular game win a whole bunch of money and then lose the next time. But on average, if you played a whole bunch of times, how much would you expect to win? Okay, so let's look at this one. So we got this mysterious card playing squirrel as pictured because I couldn't resist this picture here. Offers you the opportunity to join his game. The rules are you pay $2 to play. Okay, if you pick a spade from a shuffled pack, you win $9, and that's it. Otherwise, you don't win anything. Okay, so we want to find the expected value that you either win or lose per game. Okay, so how this works is we're going to look at all the possible outcomes in this game. Okay, we're going to figure out what is the probability of that happening, multiply it by how much money you would make or lose if that happened, and then we'll add all that together to figure it out. Okay, so let's take a look at this. So, first of all, let's talk about winning. So, pulling a spade from a shuffled pack, there's one suit out of four, right? So there's a 1 in 4 chance that you pull a spade. Okay, so this is your probability of getting a spade. Okay, and then we're going to multiply that by what you win if you get that spade. Now, you win $9, right? But don't forget you had to actually pay $2 to play, right? So your actual gain, your net gain, is only $7. Okay, so this right here, this is the amount of money that you earn if that happens. All right, now the alternative in this case, there's only one other option. The only other option is that you don't pull a spade. So there's a 3 in 4 chance, right, that you don't get a spade. Okay. And if that happens, here's where you have to be careful, right? Because you don't win anything, but you still had to pay $2 to play. So your net gain is actually a loss of $2. Okay. All right. And we are going to add those together, and that's going to tell us what the expected value of the game is. All right. So I'm doing 1/4 or 0.25, and I'm multiplying that by 7. And then we're adding to that 3/4, so 0.75 times -2. Okay, and that works out to 25 cents. So our expected value for this game is 25 cents. All right, now, here's the thing about this. The question then becomes, okay, so knowing that, what does that mean? Well, it means that if you repeatedly play this game, so if you play this game over and over and over and over and over and over and over, you're going to win sometimes, you're going to lose sometimes. You're probably going to lose a lot more than you win. Okay? But what this is telling us, what our expected value says, is it says if you play repeatedly, so if you play repeatedly, right, you will earn an average of 25 cents per game that you played. Okay. Now, as with all things, that's not a 100% guarantee, but that is what the math says. Okay. That is what should happen based on our probabilities. Okay. So if you play this game 100 times, sometimes you'll win, sometimes you'll lose. But if you play it 100 times, you're going to make 25 cents per game. So 100 times that you play times 25 cents, you'll walk away with $25. Okay. So that is what the idea of this is. Now, it might not be exactly $25. It might be a little above, a little below, but that is the idea of expected value. It gives you an estimate for how much money you would walk away with. So then the question is, if you were actually offered this game, would you play it? Okay, first of all, the answer should be yes, because if a mysterious card playing squirrel shows up and offers to play cards with you, you should 100% do that. Okay, but that aside, if this were a real life game, I would 100% play this. Okay, any kind of a game that gives you a positive expected value, even if it's just a little bit, 25 cents isn't that much, right? But even if it has any kind of a positive expected value, you want to play, okay? Because playing means that you're pretty much guaranteed that you're going to win money over time. So you're going to walk away with more money than you've spent. Okay, if you go to any casino anywhere that does any kind of gambling, you will never ever find a game there that has a positive expected value. All right, let's take a look at the next one. So, game of dice. Wow, a dice game involves rolling two dice. Okay, if you roll these particular numbers, you win $5. If you roll those particular numbers, you lose $5. Find the expected value. So, for this particular one, you don't have to pay to play. You just either have to, you either make money or you lose money depending on how the outcome of the game is. Okay, so let's take a look at this little table over here. So what this was just to kind of help us out. This is a table showing what the sum would be when you roll two dice if you get one of these yellow numbers. So like if you roll a 2 and a 5, here's a 2, here's a 5, you get 7, right? If you roll a 4 and a 1, there's the sum of 5. A 4 and a 6, there's your sum of 10. Okay, so this is just meant to make this a little bit easier. Okay, so let's take a look at this. We need to figure out, first of all, what our probability is for getting one of these numbers. So I'm going to look for sums of 2, 3, 4, 10, or 11, or 12. So here's a 2. Here's some 3s. Here's some 4s. Here's some 10s and 11s and 12s. Okay, so that's, let's see, 3, 6, 12, right? So there are 12 out of 36 opportunities where you would win $5. So I don't need to subtract anything because I'm not paying anything to play. So I just multiply that by $5. Okay, so this is the probability of a win. Okay, and then we're going to add to that the probability of getting one of these other numbers. So that's everything else, right? So using a complement, I know if there's 36 and we found 12 of them, that leaves me with 24 left. So there's a 24 out of 36 chance that you lose, in which case you lose $5. So that's the probability of a loss. Cool. All right. So then we're going to calculate this, right? When you set these up, doing this in your calculator, it doesn't matter if you do 12 divided by 36 and then times 5 or 12 times 5 divided by 36. Either way, you're going to get the same answer. So 12 times 5 divided by 36 and then plus 24 times negative 5 divided by 36 works out to your expected value of negative 1.67. Okay, rounded to the nearest penny. Okay, so what that tells me is my expected value. If I play this game repeatedly, I'm expecting to lose $1.67 per game. So if you played 100 times, right, I'd multiply that by 100 and say, oh, I would lose $167 if I played this game 100 times. Not exactly, not necessarily, but ballpark, that's a good estimate for you. Okay, so this is telling me if you play repeatedly, you lose $1.67 on average per game. Okay, that is what expected value does. So when you compare this game versus that game, right, I would definitely want the squirrel game because I'd be making money versus losing money. Okay, but here's the thing that I want you to notice about this game, right? On the surface, when you look at this, it seems like it's a pretty fair game, right? Because there's 1, 2, 3, 4, 5, 6 numbers where you would win, and there's 1, 2, 3, 4, 5 numbers where you would lose, right? So just looking at it from the surface, you look at it and you say, well, it seems more likely that I would win than I'd lose, so of course I'd want to play. Okay. And it's only after you kind of dig into it a little bit that you see that these numbers were selected so that there be more of these than there were anything else. Okay. And that is how casinos get money. Okay, because they give you games that seem on the surface like they're going to be fair and that you're going to have a good chance of winning, when in actuality, if you look at them behind the scenes, you're guaranteed to be losing money. And if you're losing money, the casino's making money. Okay. And like you could play this dice game and you could get really lucky, right? You could play 5 times in a row and every single time get a sum that's in the winning section and walk away with $20 and be happy, right? But for every time somebody wins, somebody else loses. So the whole idea of how a casino works is that they have tons of little games like this. And yeah, some people go in and they walk away having made money for the night. But on average, that casino with those thousands and thousands and thousands and thousands of plays of this game every night, they're making $1.67 per game. And for them, that sounds pretty awesome. All right, next one. Student plays the following game. He tosses 3 coins. If he gets exactly 2 tails, he wins $5. If he gets exactly 1 tails, he wins 3. Otherwise, lose $2. On average, how much should he win or lose per play of the game? That's what expected value is. All right, so let's take a look at this. So this one, kind of similar to how we just did this out with the dice. I think the easiest thing for this guy is I'm just going to write out a list of all the possible outcomes of flipping 3 coins, right? So you could get tails 3 times, 2 tails and then heads, tails, heads, tails, tails, heads, heads, right? And then heads, tails, tails, heads, tails, heads, 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 tails, heads, heads, heads. And that's it. Those are the all 8 possibilities. Okay, so let's take a look at our probabilities here. So if you get exactly 2 tails, you win $5. So let's see. This one would be exactly 2. That one's exactly 2. That one's exactly 2. So there's 3. Okay, so 3 out of 8 times he wins $5. Okay. All right, and then we're going to add to that. If he gets exactly 1 tails, he wins 3. So here's 1, 2, 3. So there's 3 out of 8 possibility that he wins $3. Okay, and then otherwise he loses $2. Okay, so we counted 3 and 6, and there's 8 total. So using a complement, that leaves me with 2 out of 8 chance that you lose $2. All right, so let's calculate this. All right, another option you could do is, since these are all divided by 8s for your probability, you can also kind of shortcut by just doing 3 times 5 and then plus 3 times 3 and then plus 2 times -2, right? Get that sum and then divide that by 8. That'll get you the same place. All right, so our total expected value is $2.50. So $2.50, right? That is the expected value of this game. This would be an awesome game. I would play this game for as long as they let me play it, and I would make big bucks, right? You play this game 100 times, you're going to walk away with $250. That sounds excellent. Okay. All right, so then let's take a look at this next one. So we got this raffle. So a raffle is held for charity draw for a $1,000 HDTV, UHDTV. 2,000 tickets are sold at $1 a piece. Find the expected value of 1 ticket. Okay, so this is obviously a really common thing, right? You see raffles like this all the time. So what we're going to look at is our probability of winning, right? Is if you buy just 1 ticket, so value of 1 ticket, then you have a 1 in 2,000 chance of winning. And if you win, even though it's only 1 TV, you still use expected value based off of the value of the thing. Okay, so the value of the thing is $1,000, but don't forget you paid $1 for your ticket. Okay, so your net gain would be $999, right? So that's your net gain of $1,000 minus the $1 ticket. All right, so then we're going to add to that, right, the probability of losing. Well, that means that there's 1,999 other tickets out there out of the 2,000. And in that instance, you lose $1. Okay, so let's take a look at our expected value. So again, since the denominators are the same, I can do 1 times 999 and then -1 times that number. Sorry, for some reason I can't say it right now. Right, so that works out to negative 1,000. We divide that by the 2,000 in the bottom. Okay, so that works out to negative 50 cents. Okay, so that is the expected value of one ticket. Okay, now here's why raffles work. Okay, the reason why raffles work is because for any given person buying a ticket, right, you're risking $1. And on average, if you bought a whole bunch of tickets, you'd lose 50 cents a ticket. Okay, which is, it's not that big of a deal, right? You're out some money, but it's not the end of the world. Okay, so for any given person, it's like, okay, yeah, this seems reasonable. Like, I'm out $1, I'm out 50 cents, whatever, right? But for the person who's running this raffle, okay, that negative 50 cents, that's from the consumer's perspective. That means that the people running the raffle, they're gaining 50 cents, right? And they sold 2,000 tickets, right? So 50 cents times 2,000 tickets, they just made $1,000. Okay, so that is the beauty of a raffle. That's why they are so common and why you see them so often. Okay, yeah, because it's an easy way to make money. All right, last one here. Game consists of rolling a color die with 3 red sides, 2 green sides, 1 blue side. A roll of red loses. Green pays $2. Blue pays $5. It costs $2 to play. Would you play or not? All right, so let's see. A red side, there's 3 red sides. So 3 out of how many total? 6 sides on a dice, right? So there's 3 out of 6 sides that are red. Okay, and if you get red, you lose, which means you paid $2, so you're out $2. Okay, green. All right, there's 2 green sides, so we're going to add to that 2 out of 6. And a roll of green pays you $2. But if it pays $2 and you paid $2, you just broke even. Okay. And then there's 1 blue side. And a blue pays $5. You paid $2 to play. So your net gain is $3. Okay. So 3 times negative 2 would be negative 6. 2 times 0 is just 0. We'll skip that. 1 times 3 is 3. And then divide that by 6. So the expected value for this particular game is negative 50 cents. So knowing that, would I play the game? Probably not. Like, I mean, I guess I would play if it was like a friend or something, or if you just are like, wow, that sounds like a really fun game that I want to play. And I don't mind if I lose money. I just want to have the joy of experiencing it, right? Then yeah, sure, play, right? It's not that big of a loss. Okay, but if your goal is to make money, then this is not a good thing for you to do. Okay. And that is the same principle that works with casinos. Okay. So when you talk about a casino and you want to have a healthy trip to a casino, you can't go into a casino thinking, I'm going to make money, because you're not. Every game in the casino has a negative expected value. Okay. So the odds of you actually making money if you go to a casino are very low. But if you go into it and you say to yourself, you know what? I'm okay with losing a little bit of money so that I can go and have a good time, hang out with my friends, play some games, enjoy the ambiance and the experience. That's a healthy way to go to a casino. Okay. So the problem comes in with gamblers is that you get into this idea of like, well, I'll win sometimes. I got to win sometime, and you keep trying and keep trying and keep trying. And do you win sometime? Yeah. Right. Eventually you'll win. But does it make up for all the losing that you did? Probably not. Okay, so expected value, super practical. I find it really interesting. All right, and it's just figuring out how much do you expect to win or lose on average for a single game. And then you can use that to figure out how much you would expect to win or lose if you played multiple times.